All right, so in this video, we're going to look a little bit at an overview of integration by parts. So we're not going to derive the formula. We simply have the formula here that we're going to talk about how to apply it. So the basic idea for integration by parts is that we're integrating a product of two functions that are not related to each other by the result of a chain rule process. So often we're dealing with functions that are not necessarily composite functions, but even if they are composite functions, the two functions that are multiplying each other are not the result of a chain rule only. And so they're derived from the product rule. And that's how the formula comes about. Now, what we're going to do is we don't really have the full product rule. We just have part of it. And so what we're hoping is that when we rewrite our process using integration by parts, that the resulting integral is going to be easier to integrate than the original one was. Now, there are some rules of thumb for how to get us started when we choose u and dv when we have different combinations of functions. And so the first thing that we want to consider is how do we choose which function to be u and which function to be dv. Now, there is a general rule of thumb that you will sometimes encounter in some textbooks. I'm not quite sure how you want to pronounce this, LIATE or LIATE. But in any case, there's 5 letters, LIATE, and they basically stand for logarithmic functions, inverse trig functions, algebraic functions, trig functions, and exponential functions. Now, this is a rule of thumb, and the sequencing is to help you choose the u function. In the reverse order, you can use it to choose the dv function, but that more or less results in the same thing. Now, what we want to be careful with, though, is that the algebraic functions actually, there's a way to break those up. If you have two algebraic functions together, there is a clear ranking for those in terms of u and dv, and we're going to talk about that. So I put this table together. The first choice for u are the log functions. The second choice is the inverse trig functions. Now, there's really no ordering here. If you have a combination of log and inverse trig functions, you're not really necessarily going to be able to proceed very far. If you usually in most problems, you're going to see either a log function or an inverse trig function, and those would get priority for you. Part of the issue here is that we can take their derivatives very easily, but we can't integrate them. In fact, in order to integrate them, we would have to use integration by parts. So what we have instead is we should prefer those for u because they will turn into something easier to work with when we differentiate them. The third choice is the algebraic functions. And as I said, there's really 2 tiers here. Algebraic functions that have positive integer power, so polynomials, are preferred for u over other algebraic functions. So this would include rational functions or radical functions. Now, these sometimes can be integrated out these radical or rational functions, and they may be still possible to work with them, but the polynomial functions, they will definitely get easier as you keep taking derivatives. The powers will go down and eventually will disappear completely if you have whole number positive powers. But if you have fractional powers or if you have negative powers, then that's not necessarily going to happen. So they will change, but they won't necessarily get easier. And then finally, the trig and the exponential functions. Again, the trig functions, the sine function in particular and the cosine will change, but they won't get simpler. Exponential functions, sometimes they don't even really change except for a coefficient. So those are sort of your last choice. Trig functions and exponential functions tend to be easier to integrate than they don't necessarily get simpler, but at least in a lot of cases, they don't necessarily get more complex. And as long as you can integrate them by themselves, then they're good choices for dv, but not necessarily the best choices for u. Now, again, that's sort of the thing to kind of keep in mind. We don't have a full list for dv in the reverse direction because log and inverse trig actually can't be integrated by themselves. So you would have to, if you needed them to be dv, you would have to do a separate round of integration by parts. We're going to look at an example of integrating these functions by themselves, which is what would have to happen if you use them for dv. But this is the general rule. Now, this is not necessarily going to mean that every combination, if you pick them in this order, that you will be able to solve the problem. Combinations of log and exponential functions follow this rule of thumb, but they don't go anywhere. You kind of get stuck when you try to integrate with those. So this is a rule of thumb. It does not work 100% of the time, but it will work probably 99% of the time. So let's look at some examples. So an example of integrating, for instance, log x, we would choose u to be log x because I can take the derivative of it. And then what's left to be dv is technically an algebraic expression. It's 1, basically, 1 dx. If I find the derivative for u, then I need that to put into my formula. So I'll take the derivative, I'll get 1 over x, and then I integrate my dv equals dx in order to get v equals x. And then I apply my formula. This is my u, and this is my u log x. This is my v, so uv minus, and then on the inside, I have v and du. And in this particular example, x and 1 over x cancel, leave me with just dx again. This is a very common thing to happen, is that the second time you integrate, it's actually going to be something similar to the thing you already integrated before. And so that's going to integrate to just x. And so my final answer, the antiderivative of log x, is x log x minus x plus the constant. Problems that involve arctan work very similarly. So in this particular example, I have x arctan x, so I let u be arctan x. dv is x dx, so that's my algebraic function. I take the derivative of arctan to get my du, and then I integrate my dv expression, and I get 1/2 x squared. Great. So now I apply my rule. 1/2 x squared is my v, arctan x is my u, uv, minus my integral of v du. So I pulled the half out because it's not going to affect the antiderivative here, but I have x squared over x squared plus 1. I can't do this as it is, so I'm going to do a little bit of long division in order to simplify this expression. And when you do the long division, you end up with 1 minus 1 over x squared plus 1. And these can both be integrated fairly straightforwardly. And I end up with 1 becomes x, and 1 over x squared plus 1 becomes arctan x. And so my final answer, so I've got a half on everything. I've got 1/2 x squared arctan x minus this x, and plus, because it's minus minus, the arctan x. So again, this is how logs and inverse trig functions typically resolve themselves. You let them be u in your formula, and then you end up with the original function and sometimes some additional terms. But arcsine and arccosine and arcsecant, they all more or less work the same way. Now, this is an example of an integral that it contains 2 algebraic functions. This integral, you may have actually encountered it before when you covered the substitution chapter. Usually at the end of that chapter, there's a discussion of a process called change of variables. It's a little bit different than substitution, but also somewhat related. And in this process, you can solve this problem, even though it's a product, but it's not a chain rule. But in integration by parts, we can also do this problem. There are very few examples of problems that can be done with multiple techniques, but this is an example of one that can be. In the change of variable process, you would let u be the square root of x plus 1, and then you would solve for x algebraically, and then you would take the derivative to get dx, and then you would get a sub expression entirely in u. And then when you're done, you would end up with expressions that involve the square root of x plus 1 with varying powers. But in integration by parts, we're going to let u be the x. Again, this is a polynomial, and so it differentiates very nicely. And then because this is a linear expression under the radical, then we can integrate this without too much difficulty. Technically, it does require substitution, but it's a substitution that doesn't really do anything. It doesn't produce, even in this case, extra constants. It's just a power rule, basically. So I take the derivative of x, I get dx. I do the antiderivative of the dv expression, and I get x plus 1 to the 3/2 power with my 2/3 coefficient. Putting that back together again, I've got, and again, I rearranged this here to put my u inside the dv, or what is now v, and then I subtract my dx, which doesn't really do anything, and this expression, and then I just apply the power rule one more time, and then I end up with my final expression involving the 3/2 power and the 5/2 power. Now, if you're comparing this to your answer when you do this with the change of variable process, the answers will not look exactly the same, but it turns out they are, in fact, algebraically equivalent. You can factor and recombine your integration by parts expression to get it to look like your change of variable process. And you can also graph them, and you can see that they actually are equivalent to each other. They just look a little different. And then the last example here that we're going to do involves another combination of algebraic expressions. We have x and x plus 3 quantities squared. Now, as you can see, x plus 3 quantities squared in the denominator here, this is a rational expression, and it's a power rule, but it has a negative exponent. So that is not the best choice for dv. It is not the best choice for u. It is a better choice for dv, because when we integrate this, the power will come down. So we take the derivative of x, we get our dx again, we integrate this, and we get our v, and then we recombine them into our formula. And because when we took the derivative of x, the x went away, our second integral is now just this x plus 3 by itself. And that is easy enough to integrate. We get a log. Now, you can, if x is positive, then you don't need the absolute values. But technically, you could have the absolute values here as well. So again, we can continue with examples involving x and e to the x and things like that. They will resolve themselves, not necessarily by simplifying, but the powers of the absolute value of the x will eventually disappear, and you'll eventually just be left with the sine x or the e to the x or whatever that second function is, that is very similar to this. Now, another example that we could look at is a situation in which, again, we have this general process, but you may have to integrate by parts more than one time. And so this one additional example we're going to look at, again, algebraically, we're going to let x squared be u, and dv will be the e to the x. That follows our rule of thumb. The derivative of x squared is 2x, and the antiderivative of e to the x is e to the x. And then following our formula, we have our u and our v minus our our v du. And so we end up here. Now, this is not something that I can integrate right now just by itself, but I can do by parts a second time. And so just following the same process, I'm going to let now x be u, and again, dv is the e to the x. Now, if I take the derivative, I get dx, and v is e to the x again. And you need to be careful when you do this about the way that your coefficients apply and the negative signs pass through. But inside this integral, this has now become x e to the x minus the e to the x, which I can easily integrate as e to the x. So again, the process did work. I just needed to do it more than one time. And when I distribute the -2 through here, I end up with 2x e to the x, and 2 e to the x is my final part of my final expression. Now, if you have a polynomial times your e to the x or by your sine x, then what you would expect is that you would just keep doing this until the polynomial disappeared. So if you have an x squared, we had to integrate by parts twice to get this to simplify out. If I had x to the 5th, then I would have to do this 5 times. Now, one of the things we're going to look at in another video is how to do several steps of integration by parts, in some cases very quickly, using a tabular method. I'm going to save that for another video because that is a special technique, and it applies in many fewer circumstances. Typically, it doesn't work when things like some of our previous examples where things simplify on the next step or things like that. So you have to choose your things for the tabular method very carefully. But when you have to do multiple steps, it can be very convenient. And so we'll come back to that in another video. But again, just because you did it once doesn't mean that that's the only time that it's either going to work or it's not. You may need, in some cases, to do multiple integration by parts steps. Now, we didn't see a lot of examples in here on like sine and cosine functions. That's because depending on the kind of function that they're integrating with, they can create some additional problems. And so I'm going to save some of those for some additional videos.